My name is Charles Lively, and I'm a science engagement engineer here at NERSC, along with my counterpart, Lippy Gupta. We are engineers in the user engagement group. And Lippy, you want to share a little bit of information about yourself? For me, my background is in high performance computing. I earned my PhD from Texas A&M in computer engineering. And I focus on performance modeling and optimization of applications.
Hi all, sorry, I'm having technical difficulties. I'm supposed to get a new laptop here real soon. I'm Lippy. I am a physicist by training, so my PhD is actually in physics. And then I did my postdoc, my first postdoc right out of grad school at NERSC, working on scientific computing. And that's kind of how I transitioned into my current role. So now I just work with Charles to help other scientists make use of our amazing supercomputing resources at NERSC. And I love it.
Yeah, nurse is a great place to work at. So, great people, you always get to learn something. So thank you, Lippy. So I would like to welcome all of you to today's community call. It's going to be a pretty interesting one, and it focuses on understanding what it takes to become an early career award winner at NERSC. And so a little bit overview of what we'll just go through. We'll introduce our award winner panelists that we have here today. Briefly go over the award nomination process, and then we'll proceed with an interactive discussion. Well, then we'll have our brief presentations from each panelist and proceed into our interactive discussion as well. And so we have here today, and let me just make sure, Kyla Davila. Kyla,
Hello.
hey, welcome. Thank you for joining. So Kyla is a third-year PhD student at UC-Berkeley, and she is a award winner for the 2024 year. And we also have Ronald Kouski. Am I saying your last name right, Ronald? Ron?
It's Kouski. Sorry.
Okay, awesome, awesome. So thank you for joining again. Ron is a graduate research assistant at Iowa State University, and you're actually working on your master's now or finishing up your master's. Is that correct?
Yep. Defending in the summer.
Awesome, awesome. Congratulations, or
Thank
early
you.
congratulations. And then do we have Max Massimiliano with us? Okay, well, perhaps he will trickle in a little bit. But what we'll go ahead and do is get started. Um, First, before we do proceed into our talks from our winners, um, I wanted to give an overview on what the Nurse Early Career Award is and the purpose and an overview of the nomination process. And so the goal of the Nurse Early Career Award is to recognize researchers that are working on advancing science through high impact computational work using our computing resources that we have available at NERSC. And general requirements for this award are just being within 10 years of receiving your highest degree and having active and recent publications and resources that have been used through NERSC for scientific discovery. And so the selection criteria that we use in selecting the winners for out of our nominees, we focus on effectively three strong areas. And that's the scientific impact and innovation of the computational research, how effective the nominee has utilized nurse resources and services, as well as understanding how the uh, how the nominee has their research contributes to the broader scientific community. And that's i.e. through publication, tool development, and other avenues as well. Okay. And so what we will actually do now is we will go ahead and allow for our panelists to, I'm going to make Kyla a co-host as well as Ron. I will stop sharing. And Kyla, would you like to just go first and kind of give everyone an overview of your background and your research work? You're muted, Kyla.
Okay, great. Can you all see okay?
Yeah.
Okay, great. So yes, again, my name is Kyla. I am a third-year PhD student at UC-Berkeley. I study Earth and Planetary Science. I was also an undergrad here at Berkeley in chemistry. And so I like to tell people that I didn't get into anything computing related until COVID, when we could no longer get back in the chemistry labs, and everything shifted, and I took my first computational chemistry class, and the rest is history. So I think we would all agree that simulations are a very fun way to do science. So of course, I'm really honored to have received the Early Career Award, and it's cool to be able to chat with you about my experiences doing research with NERSC systems. So most of my work focuses on atomistic simulations, which I do to study material properties at extreme conditions. So primarily this focuses on really extreme temperatures and pressures that we find in planetary interiors. Specifically, I study Uranus and Neptune. And so simulations are an amazing way to do this work, because often these conditions are such high pressure and temperature that we cannot observe them in lab settings. And so really our only way to access these thermodynamic conditions is using simulations. And so by doing so, we're able to learn a lot about how planets function and what they're made of. And so these atomistic simulations, you can run over a really wide range of compositions and pressures and temperatures. And so this tells us things like what materials are stable inside planets, and then more importantly, how they behave. So phase separations, transport properties, etc. Another project that I've been doing at extreme conditions is studying shock conditions that arise from giant impacts. And so giant impacts have often been suggested as one mechanism for delivering both energy and materials to our planet for prebiotic synthesis. So think things like sugars, amino acids, phosphates. And so by training machine learning simulations, we can use interatomic potentials that allow us to run these simulations at enormous time and length scales, which is what actually enables us to observe these really large polymers forming. And so once we have all of this material science done, we're working now on kind of plugging this into a pipeline that goes from our material science into then doing planetary interior modeling, which plugs in all of our equations of state, etc. And so you would get a figure something like in the middle, where you get pressure, density, composition. And once you have that, what I'm also doing, you can plug this into magnetohydrodynamic simulations. And so this allows you to study fluid flow in planets on a really global scale. And this helps us understand magnetic field generation for these planets. So it's been really amazing to be able to do these simulations on a huge range of length scales, from atomistic to planetary. And it's been great being able to get the computing resources to do that, because obviously all of these are quite computationally expensive. Okay, so then getting back a bit into the programming languages that I have used, I will start with a disclaimer that I do not do much of my own code development. I primarily use and then edit established codes, and then really write my own kind of scripts or outer layers to do data analysis. But I would say that of the codes that I use, they would fall into three main categories. So the first is that those that require a high degree of parallelization, really they're based on C++ or Fortran. And so this is really foundationally important for any of our molecular dynamics simulations, because you need to be able to calculate forces on many thousands of atoms all at the same time. And this is perfect use of parallelization. Then I would say Python is probably my preferred. It's so easy to use. It's great for simple scripting, plot generation, reading in data. It has so many amazing data science libraries. And I would also say I'm starting to see a lot of codes have kind of this outer shell of Python that users interact with, and that is then ported into C++ or Fortran to actually run the simulations. And then finally, I do have a soft spot for Bash when doing data extraction and analysis. So all of the codes I'm listing on the left, like molecular dynamics and MHD codes, machine learning codes, all of these produce these just enormous files, like many, many gigabyte files. And so the ability to just like almost instantaneously parse these for the data that we need is why we all love Bash. And so this has been really helpful as well. getting into challenges and lessons learned. Um, Again, perhaps because I don't do much of my own code development, I haven't extensively had issues with different codes. So I thought maybe instead I could focus on what I would say has been the biggest time sink of my PhD so far, which has been getting machine learning to cooperate. So I think that machine learning is so hot right now, especially in material science, because it enables you to run simulations for so much longer, so much larger systems. And this allows you to study material properties that you just cannot study on the time and length scales of traditional methods, which is really opening a new generation of material science. But that said, it's not actually easy to get these codes to work. And so I think people try and, they think, oh, machine learning is so amazing, let me try it. But I would caution against doing machine learning unless your application genuinely requires it. Because if you just want to run your system for 10 times as long and 3 times as big, it'll certainly take less time to just do that the traditional way than to figure out how to get your machine learning to work to do it. Another issue I have had is the different kind of methods of machine learning that are popular. I think neural networks have become really popular in recent years because they do act as kind of this like black box where like certain data goes in and just like success comes out. But I think this really is not often the case. And with neural networks, it can be really hard to tune your network parameters or even know how to tune them. So I guess I would suggest, and really a lesson that I have learned in choosing machine learning methods is to choose a technique that incorporates as much real physicality into your models as possible. So kind of a counterexample to neural networks, I've been using a code called chimes. And so this actually calculates energies as a function of n-body interactions. So like 2-atom interactions, 3-atom interactions. And so if you want to improve your code, there really is a natural direction, or improve your fitting, there's a natural direction to do that, which is adding higher body interactions. And also you can easily tune the precision of different atomic interactions. Oh, oops, sorry. Am I still sharing? Sorry.
Still good to go. Well, it's showing you're a
Okay,
little smaller now. Yeah, not you.
okay. And then finally, just looking ahead, some things that I want to work on are getting my peers and my group mates to get more of their material science and their planetary science codes actually working on HPCs, maybe even parallel design to GPUs, which has been incredible for my productivity. So I think a lot of people will run their planetary science codes for like a dozen hours on the login node or like days on their computer. And I think they really need to get more transitioned into getting onto the systems like NERSC. Also, interestingly, with machine learning, we're seeing that our simulations have increased in scale by many orders of magnitude, but then our codes that simulate or is that analyze our simulations afterwards have really not kept up. So you might be able to run your simulation and get 1,000 times more data than with traditional methods, but then we don't have our post-analysis codes edited so they can actually take in this much data. So I think that's a current issue we're seeing in material science. In terms of career impact, I would say that being able to become competent with a number of different codes, a number of different programming languages, has really given me the confidence to reach out to other people. I think as a grad student, a lot of older scientists are very eager to hand you their half-done codes or their codes that they haven't touched since the 90s and say, like, you may use it if you can get it to work, but I don't have time to fix it for you. So actually being able to take these codes and get them to work really helps you get a lot more cool science done. And then maybe just in terms of parting advice, I would really encourage just doing as many simulations as you possibly can. Like sampling as many conditions, etc. I think this allows you to study more systems, more conditions, and I would even say, people might say, oh, what if they're all bad simulations? There's something wrong. The more simulations you run, the quicker you're going to realize that. I'd also really recommend, again, just developing skills to being able to manage a high volume of simulations. So part of this really automated process. And then finally, developing these skills in Fortran, C++, Python, etc., will give you a lot of portability to be able to work with other people. That's all I got. Thank you again so much for the honor of the award this year.
Thank you so much for giving us a high-level overview of your work. Um, how have you been able to, if I can ask you a question, how have you been able to most efficiently make use of your compute time without, simulations can be costly. So how do you smartly make use of your computational time that you've been allocated? What are some strategies that you maybe focus on?
Yeah, absolutely. So I think before I start any long-term simulation, running a number of tests in terms of what's the most efficient speed up versus number of nodes is really helpful in optimizing my own time versus the hours that we've been given. Certainly running on the flex queues when available um, has enormously stretched the amount of computer time that we've been given. In the past, any moment that NERSC has said like, oh, Perlmutter is free this weekend, it's a great way to get a huge number of hours running. Um, and then I forget the name of the queue that's free once you run out of hours. But that one is really incredibly helpful even still. I think especially towards the beginning of the year when you run out of hours, you still get a lot of simulations pushed through that way.
So on you since you've done so many simulations, what would you say is depending on the data size, how long does a typical simulation for your work take to execute?
Oh, sure. I think that this ranges enormously in scale. If you're doing the very high theory electronic structure calculations, you might need up to like 50 hours using 2 nodes for a simulation to complete. Um, if you want to do something like the planetary scale fluid dynamics simulations, this could take hundreds of hours on like 8 nodes to complete. But then, of course, I think you're likely to run a lot fewer of those. The material science ones, you're much more likely to run in a suite of like 50 to 100 simultaneously.
Interesting. And so with the applications that you work with, how have you looked at maybe different ways to optimize them to get your simulations to run faster, or is that just a little, you're just trying to get the data at this point?
I definitely have really appreciated in the last few years Perlmutter coming online and the GPUs becoming available. That was just incredibly helpful with all of the material science simulations, either using density functional theory, which is the very high level, or using especially machine learning. So I think we got like something like 100 times speed up on the machine learning simulations with the GPUs, which was
Wow.
amazing. Um, yeah, I do think that it's something that I need to get more into is doing um, CUDA coding to get more of the codes that I'm using parallelized on GPUs, because I think that there is kind of this backlog of codes that were written like 10 years ago that would be perfect candidates, but have not yet been translated there.
Did any of our participants have any questions specifically for Kyla? And we'll have more question and interactive discussion at the
Uh,
end of the.
can I ask a question here or should I? Okay.
Yeah, go ahead and ask.
Hi, I'm Maitri, and thank you, Kyla. I work in a very similar field as yours, so I was really excited to see that you got the award this year. Congratulations. My question is, how was the application process for this award? Like, was it nominated by your advisor or was something that you had to go through?
Yeah, hi. I think we actually met in Rochester a few years ago. Um, on my end, it was a nomination from my advisor. So I don't think that there was actually anything I personally had to do. I think it was all from my various advisors. I believe it required 3 different letters.
Yeah, typically the process will be we have had people that nominate themselves, but most of the time it'll be like Kyla, her advisor, or if you worked with someone on a project that will nominate you. And typically the nominee the nominator has to give us a write-up about why they believe the nominee is appropriate or deserving of the award. Typically, will include things like their resume, publications, and then we often require at least 1 to 2 letters of recommendation. We always say the more the merrier. 3 to 4 is always good as well. And then from there, we have a panel of our NUG executive board members that participate in doing the reviews of all of the nominees, and that's how we select the winners. And so this year we had about 54 nominees, and we selected 5 winners. And so the winners that we did select represented what we thought were the best of all of those nominees. Thank you for the question. And did anyone else have a question for Kyla? Okay, well, if not, we'll open back up for questions again at the end of the meeting. But Ron, are you ready to go ahead and take the floor and give your talk?
Absolutely, yeah. Okay, yeah. See real quick. Awesome. Can you guys see the screen? All good? Awesome. Yeah, so I'm really grateful to be here and get to talk about my research. Really honored to be awarded with the award. I'm a little nervous too, so I hope I can get through this and you get to talk a bit about my research journey, which has been really exciting. So yeah, I'm a concurrent master's student in meteorology at Iowa State University. So I started my undergrad in 2020. And then I ended up getting enrolled in the concurrent program where I started my master's into my spring of my junior year. So I kind of did undergraduate courses while I was also doing this research. But it's been I loved research. I didn't really know what I was getting into, and now I'm here and I just get to, it's been so much fun, all the data analysis, all the running simulations. So my master's thesis is looking at the influence of African easterly waves, which are these synoptic disturbances that form off the African easterly jet. And basically our research question is we wanted to see what would happen if we actually suppress African easterly waves. And this is in context to tropical cyclones. So tropical cyclones need what we call low pressure disturbances in order for them to form. So African easterly waves provide this low pressure disturbance most of the time in the North Atlantic to actually form the tropical cyclone. So they're really important in terms of their climatology. So our kind of question we wanted to ask was specifically what would happen if we actually suppress the African easterly waves in our lateral boundary condition of our regional climate model simulation. So in order to analyze that, we more so wanted to look at the tropical cyclone frequency, the tracks, and then also the landfall. So in order to answer that, we used large 50-member ensembles. And we did this over 5 different Atlantic hurricane seasons. So we did 2 above average, 2 average, and then 1 below average to see kind of how this might vary in different years where conditions are more favorable for tropical cyclone development. And so when we ran all the simulations, we basically found that when we actually suppressed the African easterly waves, we saw an uptick in Atlantic tropical cyclone frequency, both for the non-landfalling, but also more notably the landfalling tropical cyclones. So we saw anywhere from a 16 to 44% increase in landfall tropical cyclones, which is pretty robust. And this was across our 50-member ensembles across all years. So, it's really robust results that we were able to get from this. So on top of that, we also saw that there was an increase in the mid-tropospheric moisture, which would kind of correspond with an increase in the favorable and environmental favorability of tropical cyclones. And in terms of the tracks and landfall, we're able to see on the bottom right here, we have the probability differences. So my co-author, Mike Reiser, basically created probability distributions of tropical cyclones occurring in each grid point across the North Atlantic. And then we did this for both the AW suppression ensemble and then the control ensemble. And then we basically subtracted the AW suppression and the control. And then so if you kind of see the increase in probabilities kind of denotes we're seeing increased probabilities of tropical cyclones in the African easterly wave suppression ensemble. And those grid points, and then blue, it's vice versa. We see more higher probability of tropical cyclones from the control ensemble in those grid points. So you can kind of already see that we're seeing these really large significant changes in landfall, especially in the Caribbean islands, the Southwest Gulf, as well as the eastern coast of the U.S., especially in Florida. So that's kind of an overview of my research. I've been able to go to a couple conferences. We're actually going to publish. We're submitting this for publication in the next week or two. So I'm really excited. My advisor's really excited about it. But we've been able to go and talk and did a poster and oral presentation at a couple conferences. It's been really fun. It's been great to hear what people have to say. So I'll talk about my programming language. I use my workflow. So really, I use a lot of Bash and a lot of Python. So I was working with, like I said, 10 members of 50-member ensemble. So this is 500 simulations or around 300 terabytes of data. So a lot of data I'm working with. I was able to get 50 terabytes of data in my Scratch directory from NERSC, which was super helpful. If it wasn't for that, I probably wouldn't have been able to do what I've been able to do with my project. So I'm really, really grateful for that. So things such as pre-processing, so creating and copying the directories and the code and linking the correct input files, running the model, so continually checking the status and then rerunning the models that that would fail integration, which kind of happened every once in a while with our climate model simulations. And then of course the post-processing is backing up the data, running the TC tracker algorithm that was created by one of my co-authors through Python, and then our post-processing program we used, which was ARW Post. So I did everything manually for the first two ensembles, and this was so much work. So I was thinking, I'm like, I got to figure out a way to kind of go through and kind of automate some of these tasks so I can be able to just kind of run them by themselves and kind of automate it. So that's where Bash kind of came in and was really helpful. And then in terms of my data analysis, I did it all mostly using Python. The TC tracker algorithm I used to run across all 500 simulations that was created in Python by my co-advisor, and I went through and did some edits to work through some of the data, and it basically spit out CSV files containing, coordinates, timestamps, and intensity parameters for 3-hour intervals for all the tropical cyclones that would form. And of course, I did my monthly averaging and my composites using atmospheric variable or of the atmospheric variables, Python, and then plotted all my graphs using Python. And I did a bunch of other kind of analysis and whatnot with how the tropical cyclones would actually form when easterly waves were actually prescribed. So all that was using Python. So going into some of my challenges and my lesson learned, the really big thing for my research was the management of the data storage. So even though I was, I had 50 terabytes of storage allocation, I was only about able to use around 35 terabytes of space to store output from simulations at a time. So those are around 50 simulations I could run at a particular time. And for each simulation, I had to basically set up the model, set up all the directories, all the, input file or input data, make sure it's all linked correctly. I had to run the model itself, make sure it didn't crash midway through. I think around I'd say 5 to 10% of my simulations would crash mid integration due to instabilities that would happen. Then I would make sure as long as the model ran correctly, I'd run the TC tracker algorithm. Then I'd do the post-processing, run ARW post, and then I'd go through and back up each simulation. And that each step kind of had these different things I had to do. I had to submit different job scripts for pretty much each one of these things, except for backing up the actual the simulations themselves. So there was a lot of lags in the time due to the queue, because the queue can kind of vary depending. I tried to do most of this stuff on the weekends, so the queue wasn't as bad. But so I had to be really proactive in monitoring all this stuff and running these bash scripts to make sure they're doing everything and making sure that I'm not missing any of the data that I'm collecting, making sure all the models ran all the way through their simulations. So like I said, the big solutions with this was creating bash scripts. Learning how to write bash was a huge thing to automate a lot of the tasks and to work with these large ensembles. And of course, this is kind of what I would tell myself back if I had to go back in time and be like, you need to plan ahead and set these weekly goals. It's like, oh, that makes it, but it was so important to actually go through and really design my weeks so I can get all the work that I needed to get done. And if there are stuff that I didn't get done, and I might have to spend a couple hours in the weekend going through and doing that to make sure I hit my weekly goals, because we're kind of on a time crunch, my master's thesis. So that was kind of the big thing. Another thing was the management of computational time and resources. So I was running a lot of simulations. So it was around 10,000 node hours that I used for all my simulations. And so I kind of had to prioritize and use certain libraries, Python that were more faster. So some things I did that kind of helped me a little bit, saved me, a few node hours, I think. When I was doing the averaging or composites across the 50-member ensembles, I always saved the data on netcdf files, so I didn't have to go through and do all the averaging every time I ran the code. And then, of course, making the plots look really nice is a really big thing. So I would go through and I only plot like a couple ensemble members at a time when I was making my plots. So they might look a little, wonky, but I was trying to make sure like everything looks all really nice and compact, having, the right font sizes, having the right, domain I want to show, all that small kind of scale stuff. But it did help, I think, in the end with saving some computational time. So kind of looking forward, like I said, I'm an atmospheric and climate scientist. I would say I'm really into modeling. I love modeling HPC, but I really want to get invested in mastering like a low-level programming language, such as Fortran or C++. And I really want to be able to create software to do a multitude of different tasks. So things such as analyze climate or software that can analyze climate atmospheric model output, kind of like Grads does. I also want to do little fun projects such as like forecasting applications or storm chase. I'm a big storm chaser in Iowa, so help creating these tasks that can help me gain my skills that I can then use for research purposes, such as any task for any model I run. If I want to go through and add some like low level processes or functions, I want to be able to spit out certain things. You know, I really want to be able to really get into the model itself, I think, in the future, as I go down my road of my career with research. So yeah, my next goal is to go. I'm continuing on towards a PhD atmospheric scientist, and my experience with high performance computing, data management, programming languages has like been extremely helpful, because whether or not I'm analyzing convective systems that are on time and spatial scales of a couple of kilometers versus climate model simulations, having the experience with working with high performance computing and programming languages to analyze these huge data sets is super important. And it's been really helpful for me when I was going out and applying for PhD programs. So I'm really grateful for that. And I guess the big thing that I've always been kind of thinking the last few years is, what is there any other kind of programming languages that I might want to change to outside of Python, or what low level language I might want to learn. So I would say right now, as a master's student, it really all depends on the context of your work, and who you're working under, as well as your past experience. So my advice, I started out coding only just a couple years ago. So like I didn't think I was going to get into coding when I first got enrolled in meteorology at Iowa State. But then I kind of picked up and ran some code, and I realized, well, this is kind of fun. I wasn't really the best at it at the time, but I was like, this is something that could be kind of fun to do, have some be able to write code to do analysis of any kind and quantify things in the realm of atmospheric research or atmospheric science. So like I said, it depends on the context of your research. So if you're doing more statistical stuff, R might be a thing that you want to go down. My co-author who made the probability distributions, he wrote all that in R and did all the analysis on R. Like I said, I use Python because it's super easy for me to use, because I've used it for so long. It's also pretty easy to kind of pick up. It also depends on your advisor. So if you are kind of new at programming, if you want to stick with something, maybe pick up something new, maybe stick with something that your advisor is working with, because your advisor could help you because they've had the experience of working with that programming language. So it's a lot of different things, but whether or not, if you stick with Python or MATLAB or Julia, like there's assortment of libraries and research out there. So you can't really go necessarily wrong with any of those. And like I said, the big thing that I really want to do is work and edit numerical models in the context of climate and atmospheric science. So I really want to pick up Fortran, C++, because they're used a lot. And Bash, of course, can be super helpful when you're needing automation. So that's kind of all I got. I guess the big advice I'd give to people who are kind of getting into coding is like it can be a little scary, and especially for high performance computing, like it's so scary to submit your first job. But I would say, like you got to take the steps to be a little uncomfortable. Just make sure, you work with whoever you're working under, your advisor. Make sure you like check with them, make sure JavaScript looks good. You're not blow up all the Perlmutter or anything. But yeah, that's all I got. So I'm free to take questions.
Awesome. Thank you for sharing the work you've done, and it seems very exciting, and you've made a lot of progress. So again, kudos to you. Did any of our participants have questions for Ronald? One question, I'll let everyone think, but one question I do have is, do you have any strategies that you're going to put into place to kind of help with, you said that some simulations crash like mid-run. Are you building in any mechanisms or making more fault-tolerant changes to try and overcome that, so you're not, not use deplete, not miss, using your allocation?
Yeah, so that's a really good question. So when we were calibrating the model, we pick it's more so based off a time step that we integrate the model on. And I kind of talked with my advisor about it, and we picked a certain timestamp that's like it's not going to cost a lot of it's going to be able to resolve tropical cyclones and everything that we're looking at. But also, it's the least saving the most amount of computational costs. So when we were going through, well, we picked one that was I think it was around 90 time step or 90 seconds. But so we went through and we found, yeah, 90 seconds was like the time step we picked was kind of the best, although yeah, like there were certain years or certain, I guess, ensemble members or more so ensembles. If there are a lot of tropical cyclones in the model itself, it will result in more crashing than not. So like our below average seasons, it was like I think I only had one or two ensemble members out of the 100 because we had two ensemble or yeah, I guess two ensembles for 1 year. So, but the more average or the more active seasons, it was like we were getting a bunch. So I guess so when we ran the model and then it would crash, what I would go through and do is it wasn't like I was like losing all the data. I would do what we call a restart file or restart run. So we'd start back at the last timestamp that we can go back to, and then we just lower the timestamp or the time step. So we weren't like losing as much data, like we weren't losing the whole simulation, right? But so that kind of helped a bit. And I wrote some code and some bash to go through. So it would go through the entire 50-member ensemble and pick out the last file or I guess time that it would write out a file. And if it didn't see that file, then it would be like, hey, this ensemble member this ensemble, yeah, member simulation crashed midway. So that would go back and do that. But yeah, that's kind of how I went through with that. Yeah. So.
Okay, cool, good deal. Did anyone have specific questions for Ronald? So one question I do have is, do you have an understanding of what might have caused the increase in the TC when you suppressed with the African easterly waves were suppressed? Or
Yeah, no, that's a great question. So that's something that we just found out pretty recently. So when we suppressed the African easterly waves, we saw that there was an increase in mid-tropospheric moisture during the time when we saw the most tropical cyclones when we suppressed the easterly waves. So we see this change in moisture. And then we looked at precipitation, because sometimes precipitation can get you an idea of precursor, like the low pressure disturbances that we talk about. Sometimes we call them MCVSs or mesoscale convective vortices can form in certain areas, and if they're strong enough, they can spin up, and then they form in an area where there's these favorable environment for tropical cyclones. They can actually undergo tropical cyclone formation and then kind of hinder off and track away. But we think that the intertropical convergence zone is the main kind of culprit. So we looked at precipitation, the precipitation response, and we saw that there was we saw this phenomenon called wave breaking. So basically, the intertropical convergence zone would was much more active when we suppressed the easterly waves, and basically it would undergo this wave breaking process where it would basically shed these vortices into the Atlantic, and then these vortices every once in a while will end up producing a tropical cyclone. So we think the big thing is the intertropical or the intertropical convergence zone is kind of the main culprit right now for why we're seeing it. It's much more active when we suppress the easterly waves.
Oh, wow, and you've just come to this conclusion recently?
Yeah, so in the last few months, we've been able to go through it. So yeah, I created composites. So I created composites through Python to go through and then go backwards in time from when a tropical cyclone formed. And then we looked at how the precipitation and sea level pressure and the relative vorticity, which is kind of, the spin in the atmosphere, we kind of went backwards and we saw that this kind of mechanism, this breaking of these two vortices from the intertropical convergence zone, we see the most leftmost, or I guess the westwardmost vortice would actually shed off into the Atlantic and would produce the tropical cyclone. And then the control simulations, it would actually have this prescribed low pressure disturbance that would propagate into the domain and then would serve as a low pressure disturbance for tropical cyclones to form.
Interesting.
Yeah.
Interesting. Oh, and Lippy, you had a question?
I do, though I'm realizing I want to let other people speak up as well. Does anyone else have a question? Otherwise, I am happy to. Okay, just go ahead. You can unmute yourself or just raise your hand if you have a question. And actually, this is the question I'm going to pose first to our panelists, but then anyone in the room is welcome to chime in because it's sort of a self-serving question. But I'm really interested in finding out, I think both of you mentioned that you're, I mean, I think we all think we're still learning. I mean, I would say you are both, and probably everyone in this room is honestly an expert. And you probably know and are way better than you think you are at using the supercomputer. Kyla, you mentioned you want to help other people in your lab group use the machine. So you're definitely you probably have a lot of experience now, but I'm curious to know when there are situations when something goes wrong or something breaks or something's not working the way you want it to work, what is your usual path forward? How do you start moving forward once you've hit a roadblock? And in particular, if it's kind of a technical roadblock. And just for some context for this question, Charles and I both work in this space of our new user experience. So we are both really interested in how can we support scientists, especially people who are new to using HPC, become, like you guys, like experts, or at least familiar to the point where you're probably helping other people in your team, answer their questions. So that's sort of the context of what is it that Charles and I can learn from you all in terms of your sort of problem solving path when you hit some kind of technical roadblock. And so I'd love to hear both of you tell us a little bit about how you do that. And then if anyone else in the room wants to share how they do that, that would be great.
Awesome question.
Yeah, I can start off first. So I mean, for me personally, I would say the big thing is to the way that I perceive problems and obstacles is that there's always some type of solution. It's just how far back how far back does the problem go? So the big thing for me is I try to use, I guess collaborations is a big thing. So I try to talk to everybody I can to kind of understand, whether it's my office mates, my advisor, or resources online to kind of get an idea of what's happening. Trying to think of it, yeah. Using your resources is a huge thing, I think, especially as a scientist. And I think, you know, being both using resources, but also having the say, I'm trying to think of the word to say. It's easy to get down when there's a mistake or something, or mistake or an obstacle. I think the big thing is to just stay confident and understand that you know, you can solve it given time, whether, you know, it takes a couple days or even, you know, a week or two. I think, yeah, the big thing is to just keep powering forward. Yeah, that's kind of what I got. So
No, I appreciate that. And so what I'm hearing is it's like you kind of crowdsource with the people you know, and then you go back to the resources that you have, like if it's manual or the internet or something like that. So, okay, I appreciate that. Yeah, Kyla.
Yeah, I think that my answer would reflect a lot of what Ron said. Tapping into resources, people that are more experienced, Stack Overflow. One thing that I have found really helpful is a lot of established codes have GitHub sites where you can post questions. So I've been able to overcome a lot of issues that are specifically with certain programs by either doing that or by even directly contacting developers who I think are often surprisingly happy to help, especially even if you're telling them of an issue that they've not heard of before. They're usually quite happy to hear of that. Yeah, I would say the biggest challenge I have had on NERSC systems has actually been installing things, which I'm slightly embarrassed to admit. So if I could suggest one NERSC user workshop would be teaching the ins and outs of actually getting things installed and implemented on the machines.
Well, don't be embarrassed. I mean, a huge amount of our tickets are about people trying to install things because it's really like, which modules do I need? Which compiler wrapper do I need? That's super valid. And it's funny because we have talked about that for our new user training. And in some ways, it's just kind of a trial and error process. Like it's like a, you know, you try things and but that might be a good, you're right, that might be a good thing to if nothing else, highlight that this is not like this is a challenging thing. Like just installing things on a supercomputer can be challenging because these aren't. I mean, some of them are commercial codes, but some of them aren't. Some of them are written for a very specific architecture, and HPC systems are really a bespoke architecture, right? It's not like everybody's MacBook or PC or whatever. So I think that's a really good point, Kyla. I appreciate that a lot. Um, Anyone else in the room want to chime in? Like, what do you do when you're stuck?
All in reinforcement. My PhD advisor used to always tell me, like, you know, research doesn't happen in a bubble, and you know, it's important to have a group or a system of people in place that, you know, are able to help you understand your struggle. And you know, for me, I'm a person that if I'm having an issue, I have no problem asking for help. So that's what I'd rather make progress. And you know, if I ask a stupid question, if it gets me progress, so be it.
I mean, that is such a learned skill, I have to say. And I appreciated Ronald mentioning that confidence is that we forget that literally our emotional state can dictate whether our work gets done or not. Because there were times when I was starting out at NERSC and something didn't work, and I was like, "This is a me problem. Like I am stupid," or you know what I mean? And I would sit there and bang my head against it instead of being like, "No, I can figure this out. I just need XYZ piece of information from these people or these resources." So I appreciate hearing that people are more confident than I ever was in asking for help because that's such a learned skill. So that's great.
And it's taken me time to get to this point.
Yeah, yes, yes. Cool. Okay, that's really great. Thank you so much.
Did anyone else have any questions for Ron or Kyla? I think one question I also have, maybe for both of you, is how do you feel that the resources at NERSC have really helped you achieve your goals versus being able to use like a smaller cluster at your institution or whatnot? What has been the biggest benefit of being able to make use of NERSC resources for both of you?
Maybe I can go first. I would say just the wide availability of computing time has really accelerated anything that I've wanted to do, and I think has really enabled us to do so much more. And it's funny because I feel like you look at like the theses of computational material scientists from 20 years ago, and they achieve like such a fraction of the studies that's expected now. And I think that's just because the computing power we have now allows you to study so many systems, so many conditions. So I think NERSC especially has given so much time to our group that it's let us, run simulations faster, chug through more problems faster, study more things. And so I think that's really helped me get several publications out on this a lot quicker than I ever would have if I just had to keep waiting for the simulations for much longer.
Ron, did you have, you kind of touched on it a lot. Both of you touched on it in your talks too, but maybe do you have any additional?
Yeah, so yeah, NERSC like Perlmutter. So yeah, Perlmutter it's so fast. It's so the amount of computational like the power it has is just unbelievable. My simulations, I run them and they're around 8. They took around 8 hours on 2 nodes, so it was I mean pretty fast. I know I have a couple other grad students I know at Iowa State who use their the local system, and they always just no offense to Iowa State, but it's I always hear just like bickering about certain things, and it's just like I have no issues with running my models or storing data. I guess the big thing too, especially for my research project, was data storage. So having 50 terabytes, being able to go and tell people, yeah, I have 50 terabytes of space just sitting there. I can like that. A lot of people are just like, that is unbelievable that I get resources to be able to say I can do that. So it's really unbelievable. So yeah, Perlmutter and NERSC itself has just been super helpful. I wouldn't have been able to do any of this without the resources. So yeah.
Awesome. Well, that's why we're here. We're a DOE user facility, and it's our mission to help researchers achieve their scientific goals and advancements as quick as possible. And, if you ever have issues or problems, reach out for help, submit a ticket. Our job is to help all of our users. So we encourage everyone to, reach out for help. If you're struggling or you're not making progress, or if you want to figure out a way to optimize or improve your application, we have scientists and researchers that specialize in that. So, well, we're at the hour. Okay. Did we have any other last minute questions for Kyla or Ron? Well, if not, thank you both for your wonderful talks and responses to the questions. Everyone, please be on the lookout as over the summer, we'll start scheduling talks by each of our award winners so that they can give their full detailed research talk. And we look forward to hearing more about the amazing work that you guys are doing. So thank you again, congratulations. And thank you everyone for attending today. Hope everyone has a wonderful rest of your day, and tomorrow's Friday, so have a great weekend as well.
Thanks all. Thank you, Kyla. Thanks, Ronald.
Thank you, Charles. Thank you, Lippy.
Thank you so much.
Bye. Bye.
Bye.